Okay, now we're going to talk about the natural exponential function. And to talk about the natural exponential function, we first have to talk about the number e. This number is called Euler's number, and it's an irrational number and a transcendental one. So what does this mean? It's irrational like pi, meaning it has an infinite number of decimals, or in other words, we cannot write it as a fraction of two numbers. And it's transcendental. Why? Because it is not a root of a polynomial with non-zero rational coefficients. That is, we cannot create a polynomial like this that has as a root e. So this is a very special number, and it in its first appearance in math was when studying in compound interests, and that's something I think we're gonna study further in our class. It is also it's a natural exponential because, as usual, this is a number that appears or occurs naturally in nature, such as the inverses of logarithms that are used, for example, for the Richter scale. That is the one we use for modeling earthquakes. It also appears in investments, compound interests, the growth of populations, etc. So, as pi, if you remember, pi is 3.14559, etc., etc., etc. So the number e is just approximately the number 2.71828, etc., etc. So, as any irrational or transcendental or special number, this number is just called by its special name, e. So never lost sight that e is just a number. And because e is just a number, that means we can use it as a base for an exponential function. That is, this is the natural exponential function. A leading coefficient times e with a horizontal displacement with an exponent either positive or negative, and an independent term adding at the end. So as you can see, nothing has changed but the base. The pattern for run rising is the same as usual. If you run 0, you're going to rise the leading coefficient times the base. But in this case, the base is e. And everything is obtained as usual. So for example, in this one, we have the leading coefficient is 1/2. The base is e. Let's identify the new vertex. So for that, the new origin, sorry. So for that, we know that the independent term is going to be the y coordinate of our new origin. And if we grab the argument and equate it to 0 and solve for x, we're going to find the x coordinate for our origin. So the new origin is in 1,5. You also remember that the horizontal asymptote has to pass through that point, meaning that our horizontal asymptote has to be y equals 5. Now, to apply the run-rise method. Just remember that our running pattern has to be 0 and 1. Why? Because these are the easiest numbers to evaluate on. So my rise is going to be my leading coefficient times my base, that is e, to the power of 0. And as usual, any number raised to the power of 0 is 1. So this is 1/2 times 1. So this is 1/2. So if I run nothing, I'm going to rise 1 positive. And if I run 1, I'm going to rise 1/2 times e to the power of 1. And this is just e over 2. And you're going to tell me, how do I graph this? In Alex, you can use the tool to plot a point, and you are going to plot the coordinate point 1, e over 2. And then if you use the tool to plot the curve, Alex will do it for you. How do we do this in a general exercise? Just by approximating. If you know that E is 2.71, that means that the half of this is going to be 1 point something. So just write 1 point something. So if I run 1, I'm going to write 1 point something. That's approximately enough for us. So that means my graph is going to go and pass and look like this. So from that, we know that the domain, as usual for any exponential function, is all real numbers. And the range for this function is, as again, is determined by the horizontal asymptote, and if our function opens upwards or downwards. In this case, the function opens upwards. That means that my range is from 5 to infinity. Another example. This function has a leading coefficient of -3. Our base is E, and let's find our new origin. So the origin is determined by the isolation of the x variable in the argument, and then by the independent term in the y coordinate. So my new origin is going to be this, and we know the horizontal asymptote has to pass through that point. So the horizontal asymptote is y equals 5. Now, if I want to run rise, I know that if I run 0, I'm going to rise my leading coefficient, that in this case is -3, times e to the power of 0. And this is just -3 because e to the power of 0 is just 1. And if I run 1, I'm going to rise -3 times e to the power of 1. And this is just -3e. So how do I graph this? I know that if I don't move, I'm going to rise 1, 2, 3 negative. And if I run 1, I'm going to rise -3e. If e is 2.71, 3 times e is going to be 6 point something. So it's enough for me if you do 1, 2, 3, 4, 5, 6 something. You can always, if you want to, use calculator to find this final value. So my function is going to look like this. So the domain for this function is -infinity, infinity as usual, and the range is determined by the horizontal asymptote and finding if the function opens upwards or downwards. This function opens downwards, meaning that the range has to be from -infinity to 5. One last example. In this example, my leading coefficient is -2/3. And my origin is going to be 1 in the y coordinate. And if we identify our argument, we are going to notice that my exponent is negative, so careful with that. The origin is obtained as usual by grabbing the argument, equating to 0, and solving for x. So this is my new origin. I know my horizontal asymptote has to pass through this point. So that is my horizontal asymptote. And now to my run rising pattern. Remember, if you run 0, you're going to rise the leading coefficient times your base raised to the power of -0. Why minus? Because the coefficient of my exponent is negative. So this is -2/3 because e to the power of 0 is just 1. So if I run nothing, I'm going to rise 2/3. 2/3 is around here. Now, if I run 1, I'm going to rise -2/3 times e to the power of -1. And by properties of exponents, we know that this is -2/3 times 1 over e. And by properties of fractions, this is just -2 over 3 e. So this is going to be, if you plug this into your calculator, this is going to be minus 2/3 of e is smaller than minus 2/3. So I'm just going to wing it. You can use your calculator, so you know that if you run 1, you're going to write something smaller than 2/3. So around here. So I'm going to plug or draw my graph. So my graph has to pass through here, meaning that my domain, remember, you can always plug it into your calculator to find the right value. The domain is from minus infinity, comma infinity, and my range is, my function opens downwards, meaning my range has to be from minus infinity until the horizontal asymptote, that is 1. And that is it for graphing exponential functions.